Today, we're going to tackle one of the most fundamental questions in all of science. I mean, this is a question that explains the very substance of your world.
No, really, take a second and think about it. What's the invisible glue that keeps solid objects from just falling apart? What holds water in a glass, or even holds together the molecules in the very air you're breathing right now? Well, the answer is chemical bonds, and that's exactly what we're going to break down in this explainer.
And we've got a fantastic roadmap for our journey. We'll start with why atoms even bond in the first place. Then we'll look at their main strategies for doing it. After that, we'll see how chemists actually draw this stuff out, explore some really fascinating complications, and wrap things up with the subtle forces that hold it all together on a bigger scale.
All right, first up, why do atoms even bother connecting with each other? Well, it turns out they're driven by the same thing that governs so much in the universe, a relentless, unstoppable search for a more stable existence.
You see, for an atom, stability isn't about a nice house or a steady job. It's all about having a completely full outer layer or shell of electrons. Think of it like a puzzle piece. It just isn't complete until all its edges are filled. An atom with an incomplete shell is reactive. You could almost say it's unhappy. But an atom with a full outer shell, that's stable. That's content.
And this whole drive actually has a name, the octet rule. Octo, of course, means 8. And for most of the key elements we deal with, that magic number for total stability is 8 electrons in their outermost shell. This one simple rule is the engine behind pretty much all of chemistry.
And you know, we have to give a quick shout out to the chemists who first cracked this code. We're talking about the early 20th century, when G.N. Lewis and Walter Kossel, who were working completely independently, came up with these foundational ideas about electron shells and stability that we still rely on every single day.
So, okay, if getting to 8 electrons is the goal, how do atoms actually pull it off? Well, they've basically got two main strategies they can use. They can either give and take electrons, or they can decide to share them.
And this choice, to transfer or to share, is the fundamental difference that creates the two most important types of chemical bonds. You can think of it as the difference between a transaction and a true partnership.
Let's start with the transaction. This is what we call an ionic bond. In this scenario, one atom completely gives away an electron to another. Now, the atom that loses the electron becomes positively charged, and the one that gains it becomes negatively charged. And what do we know about opposites? They attract. And that powerful electrostatic attraction is the ionic bond.
What's so great about this slide is how clearly it lays everything out. See? Ionic bonds are all about that transfer of electrons, and it usually happens between a metal and a nonmetal, which creates those charged ions. Covalent bonds, on the other hand, that's the partnership model. They're all about sharing electrons. This typically happens between two nonmetals, and it results in a nice neutral molecule.
So we know atoms can share electrons, but how do they share them? How many do they share? To figure all this out, chemists needed a simple way to visualize the whole arrangement. They needed a blueprint.
And these blueprints are called Lewis structures, named after the very same G.N. Lewis we just met. They're basically simple, two-dimensional diagrams that show us how an atom's outermost electrons, we call them valence electrons, are arranged in bonds. They are an absolutely essential tool for any chemist.
Let's try to quickly map one out together. For good old H2O, water. Okay, first, you count up the total valence electrons. Oxygen has 6, and each of the two hydrogens has 1. So that's 1 plus 6 equals 8. Perfect. That's our magic number. Next, we put oxygen in the middle, since it's the one that can make the most connections. Then, we just draw single bonds to each hydrogen and put the 4 electrons we have left over on the oxygen. And voila! Everybody's happy, the octet rule is satisfied, and you've just drawn the blueprint for water.
But of course, like any good blueprint, the real-world structure has some finer details. And sometimes the plan needs a few interesting adjustments. You see, not all bonds are created equal, and sometimes one simple drawing just doesn't quite capture the whole picture.
Every single bond has its own specific characteristics. There's bond length, that's just the distance between the two atoms. And there's bond energy, which is how much force it would take to actually snap that bond apart. And a good rule of thumb is that a shorter bond is almost always a stronger bond.
But this is where things get really cool. Sometimes the electrons are a bit more, well, indecisive. A single Lewis structure makes it look like the electrons are locked into one specific place, but what if they're actually spread out?
This amazing phenomenon is called resonance. It's what happens when you can draw multiple, equally valid Lewis structures for the very same molecule. The reality isn't any single one of those drawings. It's a hybrid,
an average of all of them. So instead of fixed points, think of the electrons as a cloud of possibility that's smeared out across different parts of the molecule. It's pretty wild.
Okay, so we've spent all this time talking about the super-strong forces within molecules, the ionic and covalent bonds holding the atoms together. But what about what holds entire molecules next to each other?
These are called intermolecular forces. Now, they're much weaker than the bonds inside a molecule, but they are incredibly important. They're the whole reason water is a liquid at room temperature, and not just a gas. They are the sticky forces that operate between separate molecules.
So the most fundamental of all of these is the London dispersion force. Here's how it works. Electrons are always zipping around, right? So just by chance, they can momentarily bunch up on one side of a molecule. This creates a tiny temporary charge. This little charge can then create a similar one in a neighbor, creating a very fleeting attraction. And here's the crucial part. Even though they're the weakest forces of all, they exist between all molecules, which makes them universally important.
And that's where we'll leave it for today. From the incredibly powerful ionic bonds in your table salt to the fleeting, temporary dispersion forces holding liquids together, our entire world is built on this complex, beautiful dance of attraction. It really makes you wonder, what other invisible forces are still out there, just shaping our world, waiting to be discovered? Thanks so much for tuning in.